In this presentation, we will be talking about factors of fluid migration. Fluid migration is important for petroleum engineers. In other words, tracing the migration can result in higher probability to detect a natural reservoir. It is trivial that hydrocarbon originates in a source rock that has very low permeability and migrates until it accumulates in a trap. However, there are two main types of fluid migration occurring in the subsurface. One is primary migration, which is known as migration from a source rock to a carrier bed. The other is called secondary migration, which occurs when oil migrates and travels through a carrier bed into a trap. And our focus is going to be on secondary migration. The major factor that affects secondary migration is fluid's buoyancy. Nearly all hydrocarbons have lower density than water, hence forcing the hydrocarbons to move upwards. However, there are several factors that impede this flow direction, making it to divert. These factors are permeability, capillary pressure, and subsurface structures.
Permeability plays a significant role to control the direction of fluid migration. When hydrocarbons hits a low permeability layer, it cannot pass through it. As a result, the hydrocarbon starts to move alongside the impermeable layer because the buoyant force is still driving the motion upwards, and the impermeable layer is not allowing hydrocarbons to pass through it. Combining this with different geologic settings, it would result in different outcomes. For instance, consider the following figure. We can see that there are two shale layers surrounding a permeable layer. If hydrocarbon exists in the permeable layer, it would migrate upwards alongside the top shale layer and would continue to migrate until it gets trapped. One example of a trapped hydrocarbon is when you have a pinch-out trap that had hydrocarbons accumulated between two impermeable shale layers, whereas on this figure, the trapped shale layers is pinched out, allowing the hydrocarbons to migrate vertically until it encounters another factor that would change the migration direction.
The second factor that affects hydrocarbon migration is capillary pressure. Capillary pressure arises from the fact that when two immiscible fluids are in contact with each other, the attractions between similar molecules are stronger than the attractions between different molecules. So the attractions between oil and oil molecule or water and water molecule is stronger than the attractions between oil and water molecule. This is analogous to what would we see when we put a capillary tube in a mercury pool. The mercury level inside the tube is going to be lower than the mercury level in the rest of the pool. This is because capillary forces inside the tube is pushing downward and making the level inside the tube lower than the level in the rest of the pool. The same concept applies during oil migration. The capillary force is going to act in the opposite direction of the buoyant force, restricting the migration of the oil. Here we made a simple experiment to see the effect of capillary pressure. In the first picture on the left, we took a paper towel and allowed colored water to enter through its pore space. As we can see, the colored water only went about 2 inches from its end. In the middle picture, we did the same thing, but we used vegetable oil. And in the third picture, we took the same paper towel that was filled with vegetable oil and we tried to force the colored water to enter through it. But only a small portion went through it. This is probably the effect of capillary pressure. There are 3 variables that affect the magnitude of capillary pressure. The first variable is the interfacial tension between hydrocarbon and water, which is a material property. The second variable is the pore throat radius, which is inversely proportional to the magnitude of capillary pressure. And the third variable is wettability, which refers to the liquid that is coating the formation grains. The formation is considered 100% water wet when only water is coating the grains. Capillary pressure effect is maximum in that case. However, in mixed wet formation, oil and water are coating the grains. This lowers the effect of capillary pressure because as oil droplets migrate through the pore throat, they connect with the oil molecules that are coating the grains, forming something like a film that smoothen the migration and reduce capillary pressure effect. Here is a mathematical expression to calculate capillary pressure. P equal 2 gamma over R, where gamma is the interfacial tension between water and oil, and R is the pore throat radius. In this figure, we want to see how capillary pressure can affect a real-life situation. As we can see, there are two shale layers that are surrounding a sand layer. The oil is migrating upwards through the sand layer, but as it goes upwards, capillary pressure is increasing because the pore throat radius is getting smaller and smaller due to the salt intrusion below. If the buoyant force was not higher than the capillary forces in the pore throats, then the oil will change its direction from this side to this side here. And if there was a fault that is trapping the oil, it will be important for petroleum engineers and geologists to account for the effect of capillary pressure, as the optimum location for drilling would be here and not here.
The third and last factor that affects migration's direction is subsurface structures. It is possible that subsurface structures alone affects migration's direction. When hydrocarbons reach their destination, some traps will experience some movement due to changes in the subsurface. Normally, hydrocarbons would typically be trapped either structurally or stratigraphically. And after being trapped, hydrocarbons can experience some movement caused by either faults, which create spill points, or faults, which relocate any trapped hydrocarbons. Here is an example of how a sequence of faultless stratigraphy can have an influence on fluid migration. For instance, the process resembles a full cup that is going to get spilled over if we add more to it. This is known as Gauss's law of fill and spill. Basically, if we look at the bottom trap, it is obviously full of fluids. And if for some reason fluids are added to this trap, it will begin spilling. This point at which fluids are being spilled is called a spill point. And after that, fluids tend to migrate toward the next trap. And the whole process wouldn't stop until there is no fluid added to this bottom trap. Moreover, faults also can rearrange the trap and then fluids tend to migrate to another. For example, when fault crosses a trap, as seen here, it will eventually relocate what's inside. This may create a new destination for the hydrocarbons accumulated inside the trap. And by having full knowledge about the subsurface, it can give us a clear view of where hydrocarbons will probably migrate.